Power. It's the invisible force behind, well, pretty much everything in our modern world. We totally take it for granted, right up until the moment it's gone. And in our most critical facilities, a single flicker can be an absolute catastrophe. But what if I told you there's a hidden guardian, a surprisingly simple switch designed to stop that from ever happening?
I mean, really think about it for a second. In a hospital, a data center, any place that's truly mission critical, a power outage isn't just an inconvenience, right? It can be a full-blown disaster. So how do they make sure that one tiny electrical fault stays, well, tiny?
Well, the answer is this really fascinating, complex puzzle called selective coordination. You can think of it as the art of containing electrical chaos. And believe me, when engineers get this puzzle wrong, the consequences aren't just costly, they can be life-threatening. Okay, so this really gets to the heart of the problem. How in the world do you build an electrical system that's smart enough to act like a surgeon, to precisely remove a single fault without shutting down the entire patient? So the National Electrical Code, the NEC for short, gives us this, super official definition, the localization of an overcurrent condition. Okay, but what does that actually mean in plain English? Let's break it down. It all boils down to a really simple, elegant goal. When a fault happens, let's say a short circuit in a single outlet, you only want the one breaker that's directly protecting that specific outlet to trip, not the main breaker for the whole floor, and definitely not the one for the whole building. Everything else has to stay on no matter what. And that, right there, that is perfect selective coordination. And hey, this isn't some brand new idea. The NEC has been getting stricter and stricter about this stuff for decades. It all started with elevators back in 1993, and from there, it's expanded to cover pretty much all emergency and critical power systems. That just goes to show you how vital this has become. But getting that perfect outcome, well, it's actually way harder than it sounds. The problem is that circuit breakers are built to be fast, really fast. And sometimes they're just too fast, which creates this dangerous race against time. Okay, so this is where we get something called a 3-cycle rating. In our power system, a cycle is just 1/60th of a second. So a 3-cycle rating means a standard breaker trips in about 5/100ths of a second. I mean, that's basically instant. And that sounds great, right? Faster is better. Well, not always. That speed, that's actually the villain of our story. For the engineers designing these systems, this is a total nightmare. They have to run these incredibly complex calculations, navigating what our source material literally calls a minefield of different specs from different manufacturers, and if they get it wrong, the fixes needed after the building is already up are just astronomically expensive. And this right here, this is the domino effect in action. If that big main breaker is just as fast as the tiny little one protecting a single outlet, it's basically a coin toss which one trips first. And if you lose that coin toss, a tiny little fault in one room has just caused a massive blackout. So, the big question is, how do you fix this crazy race against time? How do you give the system a chance to make the right call? The answer is, well, it's a beautiful piece of engineering, and it's all about, believe it or not, slowing things down. The solution is a completely different kind of transfer switch. Instead of only being able to handle a fault for those 3 short cycles, this new type can withstand it for a full 30 cycles. It holds on. It buys the system precious critical time. Yeah, that's right, 10 times longer. That's not just an improvement. That is a massive leap forward that completely changes the game for how these systems are designed. The source material had this fantastic analogy for it, and I've got to share it. Think of the 30-cycle switch as a big, sturdy defensive lineman in a football game. Its job isn't to make the tackle itself, but to hold the line and give the other players, in this case the circuit breakers, enough time to do their jobs correctly. And that right there is the winning play. The 30-cycle switch just stands firm, holding that line long enough for the smaller breaker closest to the problem to trip. The race is over. The correct breaker wins every single time. The fault gets perfectly isolated, and the rest of the system doesn't even blink. So look, this isn't just some nerdy technical upgrade, okay? This shift has huge real-world payoffs that make our most important facilities safer, more reliable, and ultimately cheaper to build and to expand. I mean, think about it. For engineers, those nightmare calculations suddenly way, way simpler. For the folks who own the buildings, you're now protecting millions of dollars in expensive equipment, like MRI machines. And you're avoiding those disastrous retrofits.
But the best part? You're creating a fundamentally stronger power system that's ready for future upgrades.
And this is so much more important today than it's ever been. Back in the day, a hospital might have backed up, 25% of its total power load. Today, with everything from HVAC to electronic medical records, you're looking at 75%, maybe even more. The stakes just keep getting higher. And it's also about thinking ahead, right? Future-proofing. If you're a modular data center or a hospital planning to add a new wing, having these 30-cycle switches in place means you can just grow. You don't have to rip out and redesign the entire electrical system from the ground up. It builds that flexibility right in.
All right, so let's bring this all home. What's the big takeaway here? For me, it's about appreciating these unseen guardians that keep our incredibly complex world running smoothly. That little switch buried deep in some electrical room you'll never see is so much more than a piece of hardware. It's an elegant solution to a very complex, very dangerous problem. It's the simple innovation that ensures when one thing goes wrong, everything else stays right. And it really makes you wonder, doesn't it? What other simple, brilliant pieces of engineering are out there, silently and thanklessly holding the line for all of us every single day?